Hello, this is FlippedHarber for Precalculus. In this video we're going to talk about some polar equations and graphs, and those being specifically about lines and circles. Our objectives for this lesson are to graph and identify polar equations by converting them to polar equations. Now really we're starting to look at how to graph these polar equations. Our outline will talk about some polar equations. We'll take a look at polar graph paper, our polar coordinate system. We'll talk about circles centered on the origin. We'll talk about some lines, some horizontal and vertical lines, a theorem dealing with horizontal and vertical lines. Then we'll take a look at circles that are centered on the x or y axis and a theorem dealing with them. So here we see some polar equations. Over on the left side of the screen, these equations right here represent what we're going to talk about in this video. These equations over here are basically reserved for the next video, the next topic, but I threw them up here because these really show the way that you should be thinking about graphing these polar equations. You should think about it as r is a function of theta. Now these aren't really functions in the truest sense, but you're going to treat theta like the x variable. It's the independent variable. You're going to plug in for theta and you're going to find out what the r is, just like you plug in the x and you find out what the y value is, and then you graph from there by plotting points. Now these equations over here are going to be some special cases. We're going to change these to rectangular coordinates so that they're going to look like we're used to. Now let's take a look at something you're not used to, and that's the polar coordinate system. It's a bunch of concentric circles centered on the pole. Again, right here in the middle is the pole. Everything rotates about the pole. Here is our polar axis, the one that points straight to the right. Now this is a circle with a radius of 1, a radius of 2, a radius of 3. So this is really handy for figuring out where points should be if they're a certain distance away from the pole. Okay, that's why we do these circles. So if we have a point that's 2 units away, it's got to be on this circle. If we have a point that's 3 units away, it's on this circle somewhere. If we have a point that's 2.5 units away, well, it's got to be in between the two somewhere. And then these obviously are representing angles. This should look a lot like the unit circle, except a whole lot more circles. We have the polar axis, which is 0 radians. Then we have 30 degrees right here, or pi over 6, because really these are set up for radians, not for degrees. These subdivisions don't work out nicely in degree mode. Here's pi over 3, pi over 2, and then so on. So this is what we're going to be doing our graphs on, is this polar coordinate system. And you can just find this paper back there where you would find normal graph paper. Now let's talk about a circle that's centered at the origin. Now I'm telling you what type of graph this is going to make. But if you really stop and think about it, this equation r equals 4, it's saying that the radius equals 4. Well, that sounds kind of like a circle. But let's go ahead and change this to rectangular coordinates. First thing I'm going to do to make that happen is I'm going to square both sides. And this is just because it's easier for me to substitute for an r squared than it is an r. So now that I've got it to r squared, I just swap that out for x squared plus y squared. We talked about this in the previous video. So now you should be recognizing this. This should look vaguely, if not specifically, very, very familiar. It's a circle centered at the origin with a radius of 4. So we've changed it from this that you might not have recognized into something that you should recognize very well. Now let's graph it. If I were to graph this on my polar coordinate system, I would be graphing points that are 4 units away from the pole. So here's the pole, and I plotted some points that are 4 units away. But I shouldn't have to plot points. I know what this is going to create. It's going to create a circle with a radius of 4 that's centered at the origin. Okay, so let's take a look at a line. Now when we talk about lines here, this is not a vertical line, it's not a horizontal line. It is going to go through the pole. It's going to go through the center of the graph. Theta equals pi thirds. Well, If I want to trade this out, I don't really have anything to trade out for theta, or at least nothing nice. But if I take the tangent of both sides, now tangent theta, I can trade that out. I can actually substitute something in for that. And tangent of pi over 3, tangent of pi over 3, I can just look up what that's equal to. So the tangent is equal to y over x. We've got an equation for that. The tangent of pi over 3, that's equal to the square root of 3. So now, just some really simple algebra. I've got y equals the square root of 3x. May not really look like it to you, but this is just a straight line with a slope of square root of 3 and a y-intercept of 0. So if I were to draw that on my polar coordinate plane, I'd start at the origin and I would go up the square root of 3 over 1. Up the square root of 3 over 1. How about even better? I just draw a line that goes through on the line pi over 3. That's 30 degrees. Oops, actually that's wrong. It should be up here. Oh well. Horizontal lines. Whenever you see r sine theta, you can trade that out for y. So I've got y equals 3. Hopefully you recognize that as a horizontal line. Here's a horizontal line at y equals 3. I just went up to the third circle right here and I drew a horizontal line. Here's a vertical line. Our cosine theta is x. So I go over 3 and I draw a vertical line. Pretty straightforward. Now here's a theorem. Whenever you see r sine theta equals some number. Now it has to be some real number like -2 or the square root of 3. But whenever you see r sine theta equals a number, that is going to be a horizontal line. If a is positive, the horizontal line is above the pole. If a is negative, it's below the pole. Similarly, whenever you see r cosine theta equals some number a, it's a vertical line. If a is positive, it's to the right of the pole. If a is negative, it's to the left of the pole. Now, let's take a look at some circles that are not centered at the origin. Specifically, these are going to be centered on either the x-axis or the y-axis. Now, I'm going to go ahead and multiply both sides of the equation by r. Again, I like to have the r squared. That's cool, but I really have to have this r sine theta. That's really why I multiplied by r. Go ahead and replace this with x squared plus y squared. Replace the r sine theta with y. That's why we multiplied by the r, so it could substitute easily. And now, again, you should be recognizing this now. This is a circle. It's just not centered at the origin anymore. To figure out where the center is, I'll move that 4y over and I will complete the square. So here is something that you should be used to. It's a circle because it's x squared plus y squared. Where's the center at? Well, it's centered at, well, it should say 0, 2, not x2. It should be at 0, 2 with a radius of 2. So when I graph that, I go up to 0, 2, there's my center, and I draw a circle with a radius of 2. Okay, so here's a theorem for you. All of these equations represent circles. All of these circles are centered at a point that's on the x or y axis, and all of these circles pass through the pole. Notice that this circle goes through the pole. All of these circles do that. So I'll give you, you should probably take some time to pause the video and write this stuff down so that you can recognize as circles on the graph. Okay, so that's it. Hope you wrote everything down. It's time to get to work. I'll see you in class and I'll see you online.